Good day. Let's solve this question. A. Define power. Power is the work done per unit time. Is the work done per unit time. The SI unit of power is watt. So that's the answer to that question. We move to B. An electric car is powered by a motor. The car is traveling at a constant speed of 35 meters per second along a straight horizontal road. There is a total restrictive force of 1,750 Newton acting on the car. Calculate the power transmitted to the wheels of the car by the motor. Given force equals to 1,750 Newton, and we have the magnitude of velocity, which is the speed, equals to 35 meters per second. Now I want to find the power. Power is equals to force multiplied by velocity. And this is equals to 1,750 times 35. And this will give us 61,250 Whoop. Approximately, in standard form, we can have this to be what? 6.13 times 10 raised to the power of 4 watts. So that is the solution to that particular part of problem. That is B1. Now we move to B2. Calculate the useful work done by the motor when the car travels a distance of 17 kilometers. Now we know that force F equals to 1,750 Newton, and we have distance 17 kilometers. We need to convert this to meters. So we know that 1 kilometer is 1,000 meters. So 17 kilometers will be equals to 17,000 meters. And from definition of work done is the product of force and distance. Substituting values, we have 1,750 multiplied by 17,000. And this will give us 29,750,000. 750,000 joules. So we have this. So approximately we can have this in standard form as 2.98 times 10 raised to the power of 7 joules. So that's the solution to that part of the problem for B2. So we move to the next part of the problem. And that is B3. For B3, the potential difference, PD, across the motor, the PD across the motor has a constant value, 600 volts. And the motor has an efficiency of 85%. So given the voltage, which is 600 volts, and we also have energy efficiency, and that's equals to 85%. 85% is something as 85 over 100, and that's 0.85. That's 0.85. So from what we have there, we are going to write out the formula for energy efficiency. Energy efficiency is equals to useful power output divided by total power input. Now, substituting, we have 0.85 equals to what? Useful power output. And the useful power output is what we have calculated before. And that is equals to what we have here. At the power, we have this value. That's 61,250 watts. We're going to substitute that here. And that's our useful power input. Useful power output rather. 61,250. Then divided by the total power input. And the total power input now, that will be equals to I times V from the definition of power. So from what we have, we need to calculate the current based on the question. Calculate the current in the motor. Then we are going to substitute. We have this to be 0.85 equals to 61,250 divided by I times what? What do we have? 600. That's 600 volts. So by cross multiplying, what do we have? We are going to have this like over 1. If we cross multiply, then we have 0.85 times I times 600. So in that case, we are going to have 510 I. So 510 I equals to what? That's equals to 61,250. Then dividing both sides by 510. It means that I equals to 61250 divided by 510. Then this is approximately to be equals to 120 amperes. So that's the current in the motor, and that's the solution to the problem that is for B3. Now we move to the next part of the problem, which is C. The car in B now reaches a slope as shown in figure 3.2. We can see that the car is now traveling down the slope and still with the same speed. The car continues down the slope at the same speed as in B. State and explain the effect, if any, of the slope on what? The first one. The first one, the air resistance acting on the car. That we need to state and explain the effect, if any, of the slope on the what? On the air resistance acting on the car. Now, the first thing we need to know is this. Air resistance depends mainly on the speed of the car. So from the question, it stated that the car continued down the slope at the same speed of 35 meters per second, which is what we have here. Thus, the relative speed between the car and the air resistance, which is the car here, and the air resistance does not change. It remains the same. So from that explanation, we can deduce now that the air resistance acting on the car does not change. The air resistance acting on the car does not change. So that's the solution, or that's the answer to that C1. Let's look at C2 also. We need to state and explain the effect, if any, of the slope on what? On the current in the motor. Now, when the car moves down the slope, a component of the car's weight add down the slope, helping what? It helps the car to move forward from what we have here. And this means that the motor does less work to maintain what? To maintain the speed. Therefore, the electrical power required by the motor decreases as what? As the motor does a less work. And if you check very well from power equals to IV, Now, since the voltage we have there is constant, that is 600 volts. As the voltage is constant, and since we know that the power is decreasing, for power to decrease, then the current must also decrease. So, increase in power, or let me say decrease in power, rather. Decrease in power implies decrease in current. So we can now say that the current in the motor decreases. The current in the motor decreases. So that's the solution to the problem. Thank you.